My name is Roitman Piccoli, founder and CEO of SoftQuantus. At SoftQuantus, we are building QCOS, a quantum computing operating system designed to connect real industrial problems with artificial intelligence, high-performance computing, and quantum hardware. Today, I would like to present a proposed technology enablement model for a national railway operator such as Renfe. This is not simply a proposal to run one railway algorithm on a quantum computer. It is a proposal to provide the computational infrastructure through which Renfe's own researchers and engineers could develop, test, compare, and operate advanced optimization solutions. Railway operations involve thousands of interconnected decisions. A delayed train can affect platforms, passenger connections, rolling stock availability, crew schedules, energy consumption, and the capacity of the wider network. Railway companies already use sophisticated traffic management, signaling, and planning systems. However, many optimization problems become extremely difficult when the number of trains, restrictions, and possible operational scenarios increases. The challenge is not only creating an algorithm. The greater challenge is determining how that algorithm should be modeled, where it should be executed, how different computing methods should be compared, and whether the result can be trusted. SoftQuantus proposes QCOS as a computational enablement layer. QCOS would not replace railway signaling, traffic control, or certified safety systems. Instead, it would operate above existing infrastructure as a platform for research, simulation, optimization, and decision support. Renfe could deploy QCOS within its own controlled environment, including on-premise infrastructure, a private cloud, or an approved sovereign computing environment. This would allow sensitive operational and infrastructure data to remain under Renfe's control. The proposed model contains three components. First, the QCOS platform. Renfe's researchers would receive a unified environment for orchestrating classical optimization, GPUs, supercomputers, quantum simulators, and quantum processors. Second, integration connectors and APIs. These components would allow railway datasets and existing research workflows to be translated into workloads that QCOS can analyze and execute. Third, co-innovation support. SoftQuantus scientists and engineers would initially work alongside Renfe's research teams to formulate the first problems, build computational models, and validate the results. The objective would not be to create permanent dependence on SoftQuantus consultants. The objective would be to transfer capabilities so that Renfe's internal teams could progressively build and operate new use cases through the platform. The first pilot should be deliberately focused. For example, Renfe could select one regional corridor, one cercanías network, or a defined rolling stock planning problem. Historical operational scenarios could then be used to evaluate disruption recovery, timetable rescheduling, rolling stock allocation, energy optimization, maintenance scheduling, or crew planning. QCOS would formulate the problem, divide it into computational subproblems, and execute several solution methods. These could include mixed integer optimization, GPU acceleration, quantum-inspired algorithms, and quantum optimization experiments. The platform would compare execution time, solution quality, infrastructure cost, and operational impact. The final recommendation would remain under human supervision. Most quantum platforms focus primarily on hardware access. They allow a user to prepare a circuit and send it to a processor. QCOS addresses the wider operational lifecycle. It helps determine what should be executed, which part should remain classical, which part can use HPC or GPU resources. Is the problem suitable for a quantum experiment? Which backend should be selected? When should the job run? How should the result be validated? And how can the execution be independently verified? For a national railway operator, technological sovereignty is essential. Infrastructure, passenger, and operational datasets may be sensitive. A platform-based model allows the customer to maintain control over its data, access policies, and deployment environment. QCOS can orchestrate external computing resources when authorized, while preserving explicit information about where each workload was executed and whether the result came from a simulator, classical system, or real quantum processor. The platform is designed to avoid silent substitutions. The commercial model follows a land and expand strategy. The initial engagement begins with one defined use case and a base QCOS license. Once validated, Renfe's teams can connect additional problems to the same platform. SoftQuantus would generate recurring platform revenue through enterprise licensing. A successful implementation would demonstrate that a national transport operator can establish a reusable infrastructure for advanced computational research. The methodology could later be adapted for other railways, logistics networks, airlines, ports, and urban mobility systems. The future of railway innovation will not depend on one algorithm, one provider, or one type of hardware. It will depend on the ability to coordinate every available computational resource. SoftQuantus is building that operating layer. QCOS enables organizations to model complex problems, select the appropriate infrastructure, validate results, and preserve control. My name is Roitman Piccoli, and we are building the operating system for advanced and quantum computing.